Okay, so we started on this problem in the last video. This is what we did. We found the force of x on both sides because we know that it's gonna have to be symmetrical in order for them to cancel out. So we know that fa of x is equal to the negative of fb of x and vice versa. From there, you use the theta to figure out what those force values are in relation to each other. And then you kind of just plug them in to solve for your force B, right? Because you isolated that force A and force B, and I believe force A was given. Yeah, force A was given, so that's why you isolated force B and solved for that. So then from there, we need to, I think it also asks for something else. It asks for the magnitude of FA plus FB. That one's pretty easy. You're gonna just add FA and FB, and you know that because the X components cancel out, it's gonna end up being just the Y component. So the total force would be like FA of Y plus FB of Y. But we can then add them separately just so we can just prove that the betas do cancel out. F bx equal to 0. And we're probably going to use the Pythagorean theorem to add them both up, where f total is equal to f of x plus f of y. And all of those are squared, so to get rid of the square on the f total, then you're going to just do the square root of both sides. Then let me add in the square root. Okay, and that's just the Pythagorean theorem. Square rooting both sides. That fx is 0, so it goes away. And there we go. So then we just need to solve for f of y. Let me see if I have space anywhere. I have space over there. AY plus FBY, you know the deal. Just takes me forever to write it. There we go. So we can see that here, the adjacent side is the Y. So this is the Y, right? And it's adjacent for both of them. So if we remember our geometry, we have that little saying, SOHCAHTOA. Sorry, trigonometry, not geometry. We see that it's the hypotenuse and the adjacent. So we know we're using cosine, which is adjacent over hypotenuse. And that applies for both. Cool. So then we're gonna plug that in. I'm not gonna write that for y because I don't think I have room. FA cosine that one's theta plus, I'll just write it down here. FB cosine psi. And I'm using psi and theta because we have two different angles. So you could plug the angle right in, but in order to do it symbolically, I'm just using different symbols for each angle. Cool. So then we plug that in because I believe we know everything now for that equation. Of A, which is 405,000 Newton. Sine theta is 48 degrees. And it's degrees, so make sure your calculator's in degrees, not radians. And then you have force B, which, yeah. Six. We'll keep it rounded just for sake of having it like that. And then I found out that my computer has this neat calculator trick. So let's see if it'll show up. Oh no, it's not letting me. Yes. Article level. Okay. Feel like we're missing something. Oh, right. You know how she has you like do the angles differently depending on how it's relative to the x-axis, and I usually throw that out the window and just look at the directionality of the vectors. So because we didn't do that whole adding thing, both of these y's are in the positive direction. So they're the FB, even though it was negative, and it is negative relative to like this, right? Relative to like that. It's the opposite of FA because it's heading in the direction that's different, and that works for the X ones, but both of the Y ones, Y components are positive. So you have to just remember to make sure they're both positive so you get the proper answer. And then that gets you About 8,400 newtons. Which seems very big, but then if you look at the other two, it makes sense. And also, I think that you're towing like a housing unit in this case, right? Mm, 1,354 newtons, which becomes 1,400 newtons for the sake of rounding. Cool. Screenshot. Okay. So I know Dr. Braille teaches a bit different than Dr. C. I did recommend that he go over some practice problem, and then he pulled out that pendulum problem that we saw yesterday. I'm gonna be honest, I didn't get it very well in his calculations because he was solving in the Newton's physics version, so it was like the historical way that Newton calculated the pendulum, which I find really cool that one, he knows how to do that, two, he taught us how to do that. But I'm gonna go over what I know of pendulum problems, just so you guys can see how it looks in terms of Dr. C's teaching methods. So, all right, you have a pendulum. It swings back and forth. You would assume that acceleration from gravity is constant, right? So you always have acceleration from gravity here. But it turns out that isn't exactly the case, because as it goes back and forth, it kind of like slows down near the top and speeds up and slows down and speeds up. So velocity is changing. And depending on how this moves, it also changes. So that's what he was saying about acceleration changes for the pendulum. Sorry about that. I had to step out for a second. Anyway, here you have v equals to 0, because that's one of your max points. And then over here is equal to 0 as well. Here, your v is max. And after that, you have gravity pulling down. That's these constant. But you also have tension pulling up through the string. Right, so as you can see, like over here, tension is going this way. So the y component is smaller than at the equilibrium point. Right. So that I think that's what he meant by acceleration changes in the pendulum. And it's just the same on this side. And then something about just this is geometry. If you have two parallel lines where these two are parallel, this one and this one, if you extend it imaginary to the other, are parallel, right? So for parallel lines, you have this angle, which is the same as this angle. So just in case you ever need to solve something like that, just keep that in mind. Another thing is that the length of this string never changes. The height does change a little bit here, but those calculations usually don't matter too much. He had us look at this. So like this. And this is symmetrical, so the x on one side should equal x on the other side. So that's what I know about pendulum problems in relation to what he said yesterday. Just exit out of that. Just copy and paste. Cool. I'm just gonna continue on to another problem, practice problem. So we were doing like force body diagrams, right? So this is a very simple one from one of the practice tests. Practice. So here you have a surface, right? And it's frictionless, so you're ignoring friction. You know that this is going to be the force, the normal force, right? Because it's pushing up from the ground. And then you also have force of gravity coming down. This would be force friction, but it says it's frictionless, so there's force. There's no force. But I'm gonna write it just so you guys see where it goes. And then we draw frictionless. And then this is your force pull. Cool. So then doing what we know of x and y, you know that there's going to be a y component here and an x component here. And because the force normal matches whatever fg and any y components, then this is the only one that's going to actually move. So I'm going to do it the quick way, and I'm going to do a long way just to show you all the different parts. I don't think we've actually started friction, but friction usually relies on normal force.
Good. Got two more you're gonna do this semester.
Okay, sorry about that. Some people were passing by. Oh, of course. So basically, just what I'm saying here is you only really need f of p of x, and you know this because one, there's no friction. That means that there's no other force acting on the x direction. And you would normally use normal force to calculate for force friction. Two, the system is in equilibrium along the y-axis. So that means that sigma Fy is equal to 0. Oh. So then that means that there's no acceleration in the y direction. Cool. So then that means you can solve for this problem. Just solve for solving for p of x. Let me see if I can type this. Right, and I'm putting MA because we know that force U is equal to m mass times acceleration. That's, I think, the first law of motion. So then we have FP of x, which is adjacent, which means we're using cosine. So then that means that f of x. And if you don't know how I got to this, you can ask me. It should also be covered in some of the other examples. It's just because we use SOHCAHTOA. And we see, okay, that's your 30. You know you're doing cosine, which is equal to adjacent over hypotenuse. And hypotenuse is your pull force, so you multiply both sides by your hypotenuse to give you h cosine theta is equal to a. That h is the fp. That a is your fpx. So fpx is equal to fp, force pull, times cosine theta. I'm using that as theta. I got 433 newtons. Cool. So then from there, you know that's mass. Well, I guess we probably could have solved for that first. So that because f of x is equal to fp of x, then fp of x is equal to its component version, and that is equal to mass acceleration. Then you divide both sides by the mass. I'll write that in. And I'm just going to use different brackets so they're easier to see. Take all of that divided by the mass, which is 100 kilograms. And then this would actually be a, oh, okay. P of x divided by mass. So we know what that is. I'm gonna write some stuff in anyway, like the division here. Move this. A. All right. So then your acceleration of the system is equal to 4.3. Acceleration is equal to 4.3 meters per second squared. I'll write them squared. Squared. And that's possible because I believe a Newton is equal to kilograms meters over second squared. All right, so then when you did this division here, you double check your units. You see that you have kilograms per meters over second squared divided by kilograms, which is meters over second squared. Those cancel out. And that's what you expect for acceleration, right? Let me go ahead and take a screenshot of this. Actually, one second, let me move this in a little more. I'm taking screenshots because one, in case anyone needs to like, oh, you did something wrong here, I can look back and be like, oh yeah, I see where I went wrong. Also, it helps me keep track of what we've done. Cool. And then I think, yeah, I think that's all I'm gonna do for this one. For your drawings. Because you could also have solved for like the P and then made sure, oh, I'll do it. Why not? I'll change color though. Let's do blue. I usually don't use blue. We'll double check. Double checking. So remember in the last one, we said that it's equilibrium on the y-axis. And what we meant by that was, yeah, force, normal force here. You have normal force here, you have, force gravity here. And then you have your force Y pull. Pull. So then you know that's sigma. Get the rest. Sigma F is equal to Fn plus Fg plus Fpy. Bear with me, this doesn't let me do subscript, so you know what I mean. Which is equal to ma. Well, there's no acceleration in the y-axis, so that means it's going to be equal to 0. So then that means you have to set something, like something aside from others. Nope, that the color was. So normally we're solving for normal force. Later on, because normal force is used to calculate for force friction, and also because it's the only set force that you don't really have a calculation for. Right, because normal force kind of just depends on everything else that's around. So then that means we can go ahead and move everything over to the 0 side. Or you can move normal force over there. So I'll probably move faster. Py. Right. And then we know that Fg is equal to ma with the acceleration being gravity, so it's mg. If we're defining it positive direction and upwards, then this is going to be negative. Yeah, go for it. Alrighty, sorry about that. And then you have your FP of y, which you can see is on the opposite side from your known angle. So that means you're going to be using sine. So FP y is equal to FP sine theta. I'll just write 30. So you could do this 2 ways. You could solve for them individually right here, right now, or you could plug them into the equation and solve for them that way. I like to plug into the equation symbolically, just so that helps Dr. C see what I'm doing. And so she's a bit more likely to give me credit. In my head, that's what my logic was like then. FP sine 30. And then let me just go ahead and draw some things back in. This one's going to be sine. No. Right, because this is the opposite side, or this is the hypotenuse. We have our positive direction orientated upwards. So that's why we know that the gravity is negative. Cool. And then you just plug it in. I'm gonna go ahead and divide and solve by -1, sorry. Or multiply by -1, either way. This makes this positive, this makes this positive, and makes this negative. So from there, we're gonna plug them in. And to mass, which is 100 kilograms. Gravity, which is 9.8 kg/second squared. F of P, and you stretch this out, is 500 newtons. Sine parentheses around this 30. Plug that in, and 100. You're gonna get 1,000, F of n is equal to 1,230. Oh wait, no, because this should be negative. Always double check your negative. The reason what tipped me off is this is really big. This is like bigger than force of gravity, right? And seeing as force of gravity is the only negative force, you wouldn't expect force normal to be bigger than gravity or bigger than everything that's going the opposite direction. So that's what tipped me off that was wrong. So it's actually 7,300. And then I'll go ahead and write it in. Let's do what? And then draw it in as negative. There we go. Cool, so that's how you would solve for the normal force in this situation. And the same basic idea is used whenever you're solving for the normal force. Look at everything that's on the y-axis. If there's normal force, it's likely that there's no acceleration on the y-axis. So then you just assume there's no acceleration and you plug that in like that. Cool. So I'm gonna go ahead and clear these. Um, I wanted to do an Atwood. I don't trust that I'm rusty because normally I'll try and do problems in class while you guys are taking notes, and then I'm confident in what I'm doing. I'll just go with the basics. So it gives you the box. It's giving you the weight in terms of force. That force is just like total weight. That's just mg. Let's write that. That's what that's saying there. And then it says rope is pulled over a pulley. Wait, on the other side. And then it's asking for the force that the table exerts. So that's normal force. See if I can change the color of this. And if this weight is changing, like pull. So you have here, you have your force weight. Which should be equal to your force tension here because you don't have anything going on. And then over here you have your force box or force gravity, but both the weight and the gravity, both the weight and the box rely on gravity. So I'm going to do force box or B. And then you have the normal force from the table. I tend to draw my lines from the same point. If it makes more sense to you, you can do it here, or it's like showing it's coming from the table. I'm putting it there right now to leave space for the force tension up here. We're gonna have force tension here. Then this is your normal force. So if I remember correctly, whenever you have a continuous rope like this and it doesn't have any stopping points anywhere, then the force tension is always the same. So let me write that somewhere. So what that means is that this FT is equal to FT. I did them in different colors just so we could see them conceptually. Equal to okay. So now is where pulley problems are a little weird on the mind because you can define your positive axis, right? Define it as this. But whenever you have a pulley, the axis gets curved. So say this is your positive axis, but then it curves around this pulley. So then now this is your positive axis. So you really have to be careful about the signs that you're using. Because it curves. Right, because you're looking at how it's getting pulled. Curve. So then what does that mean for us? That means this force T here that's going upwards is negative force T here. Well, that doesn't make any sense. You have force T is equal to force T. How can that be? It's because you're here. You have the same length of rope. So depending on where you're looking at the rope depends on like, if you're looking at it on this side, then it's pulling this way, right? And if you're looking at it on this side, it's pulling this way. So it's pulling opposite directions, but the tension is never the same. And like the sign depends on where you're looking at it from. But here, you are actually just using force tension to relate this to the force of the weight. So force tension is equal to force tension. Over here, force tension looks like time. I'll just write it. force tension, which in this case is negative, is equal to force of the weight. Right. So then you actually have another force tension here. That's what I was saying about, like, it could be positive or negative, depending on like the rope. Because here the box is pulling on the weight and the weight is pulling on the box. Anyway, this, I usually just neglect that because force tension is the same throughout. And then because this force tension here, I should actually put a negative there, and that solves our issue. Oh. So you have negative force tension here, which is equal to force weight, which is equal to a force tension of the box. So this force tension is the same as, let's do it the other way. Tension, not time. Force of the weight. So that means we can solve for every tension in this box. And we're solving for normal force anyway, so we're fine. And it's all in the y-axis. So we just need, right, that means that, wow, sigma f of y is equal to force tension, which we'll show later that is the same as force W, plus f of n minus b. I should like create some notation that shows you that this is like tension. I'll just do W. And that always goes to 0. So then that means that we're going to move f of n over, which is equal to now negative, because we're going to have the negative and multiply it over like we did in the last one. W minus B. Cool. And then from there we plug it in. First I'm going to write in some notes. This one is the same as force tension. And then we're moving this over here. Then after we move that over, I'm multiplying both sides by a -1 to get rid of the negative on the Fn. Cool. So then from there, we just plug it in. Right, so it's gonna change depending on what the pulley weighs, but now you have the general formula. So I'm gonna just rearrange. Oh, no, I won't. Negative force of weight plus 77 newtons. Right, because that's the force of the box. And then you plug in for all of the weights from here. Oh no, that color was. This is FW. Okay, cool. So that was our last practice problem for today. I know Dr. Braille is, okay, I think he's a genius, but in the way that he's very eccentric and kind of hard to understand. I know some of us are more visual learners or kind of need the point spelled out for us. I know I sometimes do. So that can make working with Dr. Braille a little difficult, but he is really good at physics. And I'm sure Dr. C will come back and she's not going to quiz you on something that we don't know type of a thing. I'm going to clear the drawings. So don't stress out too much. Like, don't make Dr. Braille feel bad. He's doing his best. And he's, quite honestly, I was like, with that pulley, not the pulley, the pendulum, I'm like, oh my gosh, I remember learning about this, but this is like another way. So I don't know what my point is. I think my point is don't get too frustrated. We'll be fine. Ask me for help. And yeah. Have a nice day, you guys. Bye.